Yes. Yeah. Okay. So, good morning, everyone. So, we'll continue with the FDDT simulations today. So, I hope you all have installed Lumerical in your files, so in your computer. So, does anybody have any problems with installing Lumerical? Only you. Maybe GNC can help the guy install Lumerical in the back. Uh, yes. Okay. So as Simone mentioned yesterday, these lectures are not geared towards how to use Lumerical in general. You can find YouTube tutorials on how to do these things. But this is more about how you create your own geometries in GDS, and then you import the files, and then try to simulate what you want. That is the main difference between the YouTube videos and the workshop that we are organizing today. So just to give a brief introduction about the things that I will discuss with you guys today is I'll be discussing about finite difference time domain simulation and just calling it by abbreviation FDDT. And this is the method that is used to simulate the interaction of light with materials. And this is just like COMSOL, but this is more advanced, which I'll explain deeper in the next slides. So FDDT allows you to simulate a wide range of objects and materials and permittivity and different structures, all through 3D simulations in photonics. And in fact, when you design, you can just take out large number of devices with different parameters and just keep on testing them, but this is not efficient. So what you need to do is for faster and cheaper prototyping, you simulate a lot of designs and choose the exact parameters of your devices. And then based on the fabrication tolerances, you sweep the number of devices that you can accommodate on a chip, and then you test them. So you finally have a working device that is near to the required parameters. Now, why we need to do FDTD simulations is because it is very flexible and it can simulate any arbitrary geometry that you have. And it is very accurate because it solves just the Maxwell's equations in a grid. And it is ideal for any wavelength of your simulation because Maxwell's equation can be just, you can put any wavelength in it, and then by just doing one FDTD simulation, you get a broadband result. So you can see your how your device behaves in a broad spectrum. So this lecture that I'm going to give is divided into two parts. One is before lunch, where you'll be seeing how to simulate a directional coupler based on evanescent waveguide coupling and couple mode theory. And then we go for lunch, and then after lunch, we will look at how to simulate a bus to ring and ring to bus coupling section. This is the terahertz rings devices that generate microcom sources. And that would be after lunch. So in the this today's session is like before lunch we have like 90 minutes. So I'd be giving this lecture for around 20 or 25 minutes. I'd be very quick with the slides, and then I would be like opening a new Lumerical file just like all of you, and then do everything from scratch, demonstrate to you. Unlike like yesterday, there were many hiccups with already uploaded files, but I'll be doing everything from scratch. It will take like around 30 minutes and hopefully it works. And after that, you guys can do the same thing because I'll be very quick. You guys can try it until like 12:20 by the time Antonella asks us to leave. So I will just start with how FDDT works in general and talk about like Maxwell's equation and what is the background algorithm that Lumerical solves when you give it some simulation to run. So you guys know about Maxwell's equations, and these are the four Maxwell's equations, but then I would like to concentrate on the bottom two equations that are present over here. One is the cross product with the magnetic field. So when you give what happens is when you have any photonic device on the chip, what you're basically doing is you have like some amorphous dielectric material that is immersed in another type of material. For example, silicon nitride waveguide is present around silicon oxide. So the permittivity is the thing that is varying in this geometry on the chip. So light is just going to see different refractive indexes, and that is what we need to model in 3D simulations. So whenever you do any photonic component or design, you're just playing around with the permittivity of the material, and that is the parameter that you see over here that changes. And when you talk about the source of light that you're going to inject into your system, that would be given by your current density, and that is the moving charges that are injected into your light system. So now your photonic component should work when you have a source and a refractive index difference between your waveguide and your space. It should be able to solve it. And what you would need to do is, since you can see that the magnetic field and electric fields are coupled, you would need to solve these two equations simultaneously. And so you would solve the electric field from the second equation and then inject the magnetic field, and both are coupled to one another, and you would have a solution that is constant in space and time. But then for more complicated systems, this is not meaningful. You won't solve differential equations on pen and paper, but you need to simulate it. So the FDTD solver is the simulation software that allows you to do it and gives you the results. So to solve these matrix equations in space, first you would need to discretize your system, and then you need to solve your electric fields and magnetic fields. But then you have, when you discretize your system, the algorithm behind FDTD solves it. First, it divides your system into a set of E grid cells, they call it as. It would solve the first equation in one of the grid cells, like, for example, the green one that's shown here. And there is the adjacent E cell, whose corner lies on the center of this E grid cells. It will solve the second equation. And then it will feed this back to the magnetic field equation, cross product between the magnetic field equation, and then it would continue this, and then the light is going to propagate along the entire length of your device. So that is what is shown over here. You can see my cursor here. So you would update the D vector from the H vector that you are injected from the first equation, and then you update your electric field from D is just epsilon naught E plus P. And then again, you would go back and inject the electric field vector that you got from this equation, and then solve for the magnetic fields, and then you just continue this in a loop, and that is going to be like propagated all the time. So when you discretize your system, the partial derivatives just become like delta t, and you can see that this is the one-dimensional equations that I'm showing, that I transformed it from the cross products, and this is the discretization in the space, and this is the discretization in the time. You solve for the electric fields in the grid cell K, and then you get the magnetic field in grid cell K plus half. And in the next time step, you solve for the magnetic fields by using the electric field. You solve the magnetic fields, and then you get the electric fields in the next to next time step. So this is just another like representation of what is happening. You solve the same thing. It is represented in a diagrammatic fashion. This is the basic background of how the FDTD algorithm works and how it is going to solve. But then these things, you don't need to implement this exact differential equation. It is done in Lumerical. So first we will have a look at how the Lumerical interface looks like. I think most of you are not familiar with the Lumerical interface in general. It looks like a very old software, but then they do have a very good background algorithm that works fantastically. So many people in photonics industry still use it. So let me introduce you to the basic workflow of the Lumerical software that you need to use to solve any simulation. So what you have is, first you define your materials, of which materials you are going to use, say nitride or any like crystalline materials, MgF2 or anything that you have. And then you define your structures, any complicated structures, ring resonator, like, or a spiral, or even like WDM splitters. everything in a GDS file, and then you import the GDS file into Lumerical, and then you define your simulation region and meshing. Then you add your sources, and the analog of sources is monitors, and so that you can see what is happening when the field propagates. And then you run your simulation by checking your boundary conditions and defining how much memory requirements it takes to simulate this, and checking your simulation dimensions. Then you collect your monitor, plot the data, post-process it, and get the required parameter that you would like to see. And finally, you might not get your desired results, so you might need to update your GDS layout and import the new GDS into Lumerical, and accordingly, you might need to update your sources and monitors to these new positions. So you see that this is going inside a loop, and this is an iterative process. So you would also need to set up a sweep of parameters, and Lumerical also offers a direct way to do this. They have an option for parameterization and sweeping and optimization functions, which help you to get your desired parameters by not clicking or making new files several times. So let's start with the source. Since I said in the previous slides that in one FDTD run, you are going to get a broad spectrum of results. That is because, as the name suggests in FDTD, this is a time domain simulation, finite difference time domain simulation. So what happens is you send in pulse of light, and you're solving your Maxwell's equations on this mesh that you have created, grids, 3D grid cells. And you can see that the Fourier transform of a pulse is like a Gaussian over here. And so you would have results that are very accurate, for example, from 1.4 micron to 1.6 micron that you would be able to get from these simulations. But then if there are also several options on how to excite these pulses with specific mode index and different type of mode field diameters into your chip or your bus waveguide. For example, here I show that the electric field is maximum along the EY component. You excite the first order TE mode, or you can also like understand how your device behaves for a TM mode excitation. So I'll go to this like during the hands-on session, but then this is just the introduction of what is happening. So what you have is you have sources, and you launch it. You launch the sources into your system, and then finally you should also consider when you define your simulation region. What you want to do is actually when you go to a lab and you use the chip and you pump in light, the chip is like it's present in free space. So it's you basically need to simulate an entire infinite size system. But then this is not feasible in FDTD because you cannot just say that, yeah, I have the chip is extending until here and I have free space. I cannot just do this inside the simulation region. So what you would need to accurately model is the boundary condition. So as an illustration over here, you can see that to model an infinitely free space, you need to have an exact boundary condition that is required that can model this. You cannot have a perfectly absorbing layer because then that would cause some reflection, or just truncating the boundary would not also help, because what you would need to have is something that absorbs your electric fields, but then there would be no reflection from the boundary surface. So the way to do that is by coordinate transformation that is described in this paper over here. What you need to do is you should not have some reflection that is coming from your boundary surface, but then the field that is going to hit your boundary layer should get attenuated and die down. So this is one of the examples of so the thing that we'll be using in our session today would be a perfectly matched layer. So what the perfectly matched layer does is it absorbs all the electric and magnetic field components that is going to be incident on your surface, and it is going to attenuate the field. And no matter what angle of incidence your field is going to hit the perfectly matched layer, there will be no reflected waves that are going to be emitted from this. So for example, you see over here that this is without when S of x is 1, This is just the wave equation that you would get. And when you have S of x as some complex number, the complex number would come into the solution as an exponentially decaying function. And that is how the field is going to die. So what interesting feature that you observe here is there is no wave that is going to go in the opposite direction. So we observe no reflection when we do this transformation. And this is frequency independent when we have some conductivity sigma that is also independent of frequency. So finally, the PML will allow us to simulate an infinite space with a finite computational grid. But PML is not perfectly, it's exact. It's not very exact because what I just showed in the previous slide was just solving the differential equation. But then when we do it in finite difference time domain simulation, you have discretized your system. Just by discretizing your system, can mess up, and there might be some parasitic reflection that can occur, and there will be some error that is proportional to this reflection. And the number of PML layers is also very important, because if you have the fewer number of PML layers, then your incident field won't decay. Then it can hit the boundary of your PML layer, which is perfect electric conductor, and it can come back. So the solution would be just to increase the number of PML layers. And since there is a discontinuous jump in the conductivity that you introduced over here, you just introduce the conductivity for x greater than 0. There can be some reflection that's again introduced. So the thing is, you need to taper your conductivity profiles to accurately model absorbing PML layer. So PML is not very exact, but based on discretization, it can cause more problems, and you can solve it by increasing the number of PML layers and tapering the conductivity profile. But you don't need to do all of this. FDTD Lumerical has everything built in. So if you just choose PML, it works in general sense. But if you face some like error in your FDTD, or if your simulation diverges, then you might need to look into this. So this is the slide that I flashed earlier, but then I didn't get any questions like what would be the time step delta t that you take to solve your differential equations across these E cells. So the time step delta t just depends on the number n that is present over here. So you need, when you discretize a system, it basically depends on how many parts of the wavelength that you're taking to solve the Maxwell's equations on this grid. So it can be, if your wavelength is lambda, you can take a step. So you can discretize your grid cells based on lambda by 6 or lambda by 20 or lambda by 30. It is just going to increase the simulation time and complexity of the system. But what would be the correct number? What would be the minimum number that you would require to solve this equation is very important. So if you can just visualize what I just told earlier, how the same thing works in a one-dimensional E-grid cell in space and time. What you have over here is space in the x-axis and the time. So you have the E cells that are marked in dots over here. So you in the first time step, you would be solving, you would be updating your HY based on the electric fields that are present over here. And then in the next half time step, you would have your magnetic fields that are going to be your solutions. Then in the other half time step, you would use these magnetic fields and update for the electric fields. But so basically what you have done over here is for a propagation of delta x in space, the total time step that your FDTD algorithm took was delta t. But then based on physical considerations, this should always be less than the speed of light. So that is what the CFL condition stands for. And based on this, you can find out the number n, which is like approximately helps you to determine the step size that you would need to use for your simulations. So what I can tell you is empirically, people use like the discretization in space to be like lambda by 6 or lambda by 12. And then based on this, you can determine your time step. But you don't need to do this in Lumerical. You can just select the mesh size mesh size 1 corresponds to lambda by 6, mesh size 2 probably corresponds to lambda by 10. And based on that, it determines time step, everything in the background for you. But this is just like going into what is happening in the background. And now, so that is like basic introduction to FDTD algorithm and how it works in the background. And I see like it's already 11:30, as I promised, like half an hour of lecture. Now we would dive into the hands-on. Any questions? Okay.
Generally be a uniform structure, can be a non-uniform structure.
Yeah, so when you discretize your system, you don't just discretize it uniformly. The mesh size can also be non-uniform. So wherever you have like high density of your photonic components, you can discretize it to be like very closely spaced. And there the time step would of course be very different. So the step size can be non-uniform to answer. Yeah.
So just to understand the difference to yesterday. Yesterday we could just solve the Helmholtz equation.
Yeah.
Today we also want to treat the magnetic. Is it correct to say that it's because the evanescent coupling is basically through the moving charges?
There is exactly no evanescent coupling until now.
Okay.
So that is the tutorial. But here is just in general, just saw in Maxwell's equation on a grid.
Okay.
And if you were talking about yesterday's, I think it was COMSOL. So in COMSOL, you could have your grid cells in any shape or size, if you have noticed. But here it's mainly rectangular grid cells, because as I just showed the structure, it is set of grid cells along. So you have your electric fields along the edges of these grid cells that you are going to solve for. So here it's mainly rectangle. Okay. Any more questions? Yeah.
I didn't understand at the beginning of your slide. There is vector G.
G?
This density. When you say,
Yeah.
I don't understand why you consider the injected light as moving trajectory. Describes moving trajectory.
So basically, you need some source that is going to excite your system, and you can think it of like some polarization that is happening inside your waveguide, due to which there are some charges or photons that are accumulated. I mean, so if you want to pump any device, where would you introduce your source into Maxwell's equation? I mean, so the correct thing is like, so J is current density. So I think you're confused between why you're injecting current into a photonic component. Is that your question?
Yeah.
But then to model it, it's not exactly J that they're injecting. There is some relation between J and the pump power, optical pump power that you're going to introduce. And that can be modeled using J over here. It is not exactly J.
Okay.
It's a source. So whenever you have some source that is happening in lattice, then you model it with it. Okay. Any more questions? Okay. So now we'll move on to the hands-on session. So first I'll introduce what I'm going to do in Lumerical, and then I'll quickly demonstrate it in Lumerical, and then you guys will do it, and then we have like about 40 minutes, and then we go for lunch. So the thing that we are going to simulate in Lumerical is a directional coupler. So the thing that you see over here, as you can see, is a directional coupler. Basically what you have is a set of two waveguides. One is on the top, it is going, another one is bottom. There's a bit of gap between these two guys over here, so they're not connected. So the thing that the parameters of this device is the coupling length. the length of the region where the waveguides are close enough. This is the coupling length of these two guys. And uh, there is some coupling, there is some gap between these two waveguides, which is denoted by the gap and the geometry. So you can have your band to be like perfectly circular or just two straight waveguides that are just going to come over here and the wavelength of the incident light. So these are the parameters that are going to matter when you're simulating these devices. So you will have some light come in or from here, and I will describe what you would expect when you have two adjacent waveguides next to one another. So what happens when two waveguides are adjacent to one another and there is like very small gap in the order of wavelengths between them? Huh? Okay, everybody answer that once. I couldn't. Okay, so yeah, so the mode from one of the waveguide would just leak into other waveguide, and then there will be some light that is going to leak into it. But then when the light is going to leak into the other waveguide, it will just propagate, and then this light can also again leak back into the adjacent waveguide. So that is also possible. And so just by using this concept, you can see that if you write down the electric field equations, where E1 is the electric field in your first waveguide, and E2 is another electric field in the same waveguide, but with another mode profile, which can get excited when it is going to leak into your adjacent waveguide. You can just see that the electric field depends on the delta N difference between the refractive indexes N1 and N2. So here delta N is N1 minus N2. But what is N1 and N2? You would need to not consider a single waveguide, but you would need to consider both the waveguides that are excited at the same time and look at how the refractive index, how the mode profile is going to vary. So it's not just a mode now, we call it as super modes because you are exciting two waveguides both simultaneously. So what you would have is one to be symmetric and the other refractive index variation to be antisymmetric between the adjacent waveguide that you see over here. The blue region shows that both the refractive index are like almost the same, and the red one shows that the electric field is going to be out of phase with the adjacent one. So what we need to find out in Lumerical is the refractive index delta N difference between these two profiles. And then using this equation, you would be able to calculate that after a propagation length of L, how much power is going to be in your adjacent waveguide after traveling. So there is going to be power exchange between these two guys. And the function, when you solve the equations, you find out that it is a sine square function, and you can find out what is the length L for which there can be a power transfer of 100%. So anybody has any doubts with the concept of what we are going to do? Or like any mode leakage or anything? Like that is the structure that we'll be simulating. And then after lunch, we'll be doing bus to resonator coupling. So those are the two exercises. No questions? Okay. Okay. So for the first session, we will be doing a 30 to 70 splitter. And then I think in the evening when you have time, there is this homework session or something. At that time, you can try out the 50-50 coupler on your own. So now let me launch Lumerical. Yes. Okay. So let me just open a new Lumerical file and a model. Yeah, so everything is new. There are no changes or anything. So this would be what is present on the screen. But you guys, I would recommend you to just look at what I'm doing over here. And then you can go through and do it everything later, and I'll be going around. So first, what you need to do is you guys are going to work on different material platforms. So what you need to do is you need to get your refractive index as a function of wavelength that you need to import into your Lumerical file. So what you have is an sin.mdf file that is present in your folder that I've shared with you. You just go there and import it. So it will ask you if you want to replace other materials which are overlapping. You can just click replace everything at once. And then what you need to import is next the GDS file. So there is an option that you can see on the top of the screen. There are like different structures that you can draw or different components that you can add. But then you would be interested in importing the GDS file because you can draw any weird design into your GDS file that you usually would do, and then finally import it. So you have the option that is present on top called as import GDS, and then you can import the file, but then this is present over here. Yeah, so there is a test device _1, I think, in your systems that you can import it. And then it will ask you which material property that you would need to assign to this device. You can go down and select as SIN hours that will be present in your systems when you imported the sin.mdf file, and then click import. Let me check if it is the right one. It is supposed to be like 30 microns in length. So you can use a ruler that is present on the left side of your screen. You have like the option for cursor or deleting or like zoom in, zoom out, and pan mode, which is self-explanatory. And you can use a scale to measure the length of your device. And you see that on the bottom of the screen, you see that it is like around 40 microns. If you can see my cursor here, like the dx and dy, dx and dy is present over here when you measure it using a scale. So it is 30 microns. And then what I would need to do is next I would need to assign the height of your GDS file that you imported. In fact, when you designed your GDS file, you just gave your X and Y dimensions, but then you need to assign your height of the device that you're going to be fabricated. And this you would be like discussing with your fabrication engineer. So when you click on like right click the GDS layer and click edit, you would have some properties tab open up, and you can see over here that you can define the origin, X, Y, Z coordinates of the center of the GDS file that you imported. And in the bottom user properties, you have an option for Z span. For the Z span, you can see that there's a value with a unit micron. So this is going to be the length along the Z direction, which is the height basically. And you can change it to be the height of the device. So here we are going to use 800 nanometer thick silicon nitride. So I'm going to change it to 0.8. And the material is SIN because while importing it, I had already chosen it to be silicon nitride. And I don't want any constant refractive index, but just the material refractive index. So I can just click remove, and I have these parameters over here. And let's just explore what other properties it has. Like for example, Lumerical itself has some scripting languages that you can use to import, draw, and do everything without the interface GUI that is present over here. So this is the Lumerical command that you would need to run, but we are not interested in that. And this is also some rotations that you can use on top of your imported GDS file. So you can rotate your entire GDS file by 90 degrees either ways and look at what happens. And then I click apply and click OK. So I don't know if I explained to you, the Lumerical interface is a bit different compared to like COMSOL, Maya, or Adobe Photoshop, or Adobe Illustrator, Adobe Photoshop, where you have some 3D diagrams where you have just one screen with the perspective view. But here you can see that there are 4 different screens that pop up because one of the view is like in XY plane, the other is in XZ plane and YZ plane. So these are the 3 views that you have, and the final one is the perspective view. And I would be primarily using the XY view on the top one because I don't really need the Z direction view, but you can just close the windows if you're uncomfortable with it, or you can just close it. But usually when you open a new Lumerical file, you would have 4 windows that pop up. So now we imported the GDS layer. Next, we will need to like excite our system. So let's find out where the sources are. So we can see on the top bar is where you would need to search for the different components that you would need to add. So I can see that the sources is present over here, and there are multiple different options for excitation of your waveguide. So for example, you can have a dipole source that is excited, or Gaussian source, or plane wave, and other different things. But we would need to, I would like to see what happens for the fundamental TE mode and how the power is going to couple into the adjacent waveguide. So I'd use the mode source that is present over here and click it over here. And you see that in the FDTD layout, you have another component that has arrived. It's called as source. And you see, this is the way the source is placed initially. But then, as I showed in the slides, I want to, you can see the cursor. So I would like to see what happens when I excite the source on this part of the screen, and then look into look how much power is going to get coupled over here. So I would like to be perpendicular to the structure. So it is like around, if I see that it is like and you can look at the coordinates X and Y on the bottom right of your screen. So it's like Y equal to 36.7 and X equal to minus 45. I have almost perpendicular surface that I can get through which I can inject this mode. So let me move this source to the position. So I right click the source and click edit object, so that I go into the geometry tab to place the position of this mode source and change the dimensions and so on. Now it was facing towards the x-axis, but I want to inject in the y plane on the top waveguide. So what I would need to do is first I would need to change the injection axis so that I get the option to inject it in the y-axis, and I get an option for the x-span. If you are injecting it along the x-axis, as you can see over here, the x-span is disabled because it is 0 along the direction, basically. So once you change it to y-axis and then click apply, you would see that it is injecting along the y-axis. But then now you see that the injection axis is the source is going to be pumped in your positive direction. But then you want your source to be pumped in the negative direction. So there is a direction option as forward or backward. You click backward, you see that your source is rotated by 180 degrees, and this is where it will be injected. Now for the location, if I remember correctly, it was like around minus 52. The center, no, it was not minus 52, 42. Okay. Okay, it's fine. So, and then the expand was like the size of your mode source should be able to, like, it has to see both the waveguide as well as the silicon oxide together, right? So what you need to do is you need to have your mode source expand to be larger than the waveguide width. And the waveguide width that I have given over here is, I think, 1.4 or 1.5. I don't remember exactly, but I'd be happy with like anything expand greater than 3 micron. So you can see that it is larger than your waveguide width. And actually, there is, since this is not a completely like a software-based program, but it has a GUI, there's a wonderful option where you can just go and click the cursor, and you can move around your sources and your monitors. So I can just drag it. Yeah, when you get this option, you can just drag it and I can move it around and place your mode source on top of your waveguide. So if I just want to place it over here, I can just click over here, and you can see that in the object geometry, it has changed all the parameters accordingly. So you don't need to worry about the exact X and Y coordinates of where you're going to apply. And you see that the position is almost centered. But I have not defined the height of your source. So I see that the height of source is 0.5, which is lesser than the size of your height of your waveguide. So this can give some incorrect results. So I need to update it, and this should be greater than 0.8 micron, and it has to also see your silicon oxide present around. And if I click apply, you can see that in your X and Z perspective that actually this is not equally aligned. If you want to see it, you can just right click on the perspective of which you want to observe and click change aspect ratio settings to lock the view that you want to see. That you can just lock the X and Z over here and click OK and then zoom out and zoom in. You see that, yeah, I'm like kind of exciting it properly. But then let's again go back and lock X and Y and then zoom in and zoom out to update the settings. I see that I have excited my mode properly on top of the waveguide. And then now we have excited the source. The analog is like now we proceed and add monitors to these devices to see what is going to happen. So just like the source, there are multiple options for monitors too that are present over here. If you just click the drop-down menu, you see that I can add like move monitor or a frequency domain field and profile monitor or mode expansion monitor. We will look at mode expansion monitor after lunch. So for now, I just want to see how much power is accumulated in different waveguides. So this is the DFT monitor that I would need to add. And it just adds it along the XY plane, but then I would like to have it in the XZ plane. So again, I go right click, edit, and then go into the options for geometry. And I see that it is like a 2D normal, but then I would like it to be perpendicular to the waveguide that is present over here, which is along the y-axis. So I think I need to click like 2D y normal to get it perpendicular to the axis. Now you see that the monitor is horizontal along the x-axis, but then the location and the size of the monitor is not correct. Again, you can do the same thing, update the span to be greater than the waveguide width, and then you update the Z span to be larger than 0.8 micron, and then you click apply. But the location of the y coordinate is small, so it's actually present over here. I can just zoom in and then bring it down to the position that I want. So actually I need to have two monitors, one over here to see how much power is coupled into your bottom waveguide, and another monitor that is on top to see how much power is going to get coupled. So I can just do Control-C, Control-V to duplicate it. So I have two monitors with different names. So I can just add a monitor, call it monitor top with different names, and I can move it around. So I click apply to change the name, and you can see that it records the data. You don't need to change other tabs because yeah, you want to accumulate both electric and magnetic fields to calculate the total power. So everything is checked. That is fine. And then you have your other tabs where you just set the settings to be like default. You don't need to change other. And then I can move this monitor, top monitor to the top waveguide. I mean, I would like to have it. I would like to have it on the same Y position of this guy. So let's check what is the Y coordinate of this source. The Y was like 40.48. So I can move this monitor top again to 40.48. And click apply, but the Y was not exact. And then I get this. So the Z axis were all that were copied from the monitor, so everything looks fine. The Z span is greater than the height of your silicon nitride, and you click OK. So finally, we have our source and our monitors that is defined. So what do we do next? Sorry? Yeah, so finally, we need to define our simulation region or which we would like to simulate. So we need to add an FDTD mesh that you can add it by going over to the simulation. And there is an option called as add FDTD region. And then you click it. So you see that you've got a big mesh over here. And you can adjust the size either by, again, going into the edit object and changing the geometry, or just resizing it manually by hand and seeing how much is the thing. So yeah, so it should accommodate all of your sources and all of your monitors. And the FDTD region itself has a z-axis, which usually is not very accurate. Yeah, here it is. Yeah, the position of the z I would like to be centered around 0, and this also to be around 0, and x also to be around 0. It's fine. It need not be exact, but then the z span should be larger than the height of your waveguide. And you see that it gets updated, and you see that your source and your monitors are all accommodated inside your FDTD region. This FDTD region itself has some options like dimensions is 3D and the mesh settings that you were talking about. So for good simulation results, usually the mesh type is non-uniform. That is where you have a lot of photonic components. The grid cells are smaller so that it can get accurate results of the coupling of the electric field and magnetic field vectors in this region. So usually the mesh type non-uniform works very well. And you have mesh accuracy. So mesh accuracy of 1 like is around the least accuracy, which is like around lambda by 6. Your grid cell is like discretized 1/6 of your wavelength. And this gives you like very low accuracy results, but it runs very quickly so that you can check if your simulation is right or wrong. You don't need to wait for 4 hours and then say, I did a mistake with the injection or something. So you can run it for lower accuracy and then run it like later with higher accuracy. Usually accuracy 4 is one which you can trust your simulations for, but just for the hands-on exercise, we can use low accuracy and check what happens. And there are like other settings, like the total simulation time that your FDTD needs to run for. So the total time the total minimum time that you would ideally require it to be run for is the time that it takes for the pulse to propagate from the source and to reach the other end of your monitor, and also the other end of monitor. But then again, we are using boundary conditions over here. So we would ideally like to have all the electric and magnetic field to be absorbed so that we are sure that we get a stable solution. There can be like some reflection over here and then the electric field comes back. So we don't want to have that. We need to be sure that our solution is accurate. So we would like to have the electric fields to die down. So what we would need to do is we can set the simulation time to be very large and then say to Lumerical that you shut off the simulation automatically if the electric field or the magnetic field vectors reach like very small values, like 10 to the power minus 5 or 10 to the power minus 6, which happens after the electric fields have all died down in your entire simulation region. So that is what you see over here. In advanced setting, you see you have checked, it is automatically checked the early shut-off option with a shut-off minimum of 10 to the power minus 5. So when your electric fields reach 10 to the power minus 5, your simulation is shut off automatically. So you can indeed have your simulation time to be 2000, 3000 or large number, but then everyone will take the same amount of time because it will take the same time to reach 10 to the power minus 5. So it is ideal to have the simulation time to be very large, and 1000 works for the simulation. If you need to track it, you can add like, I'll show you how to do. But what you didn't ask me was I added silicon nitride, but then I told this material is surrounded by silicon oxide. So what we need to also define is the background medium of this FDTD region that where your entire directional coupler is immersed into. So you have an option for the background material that you can use over here, and you have an like default SiO2 glass material that is present, and you can choose that and click apply. So we have now both two materials. One is silicon nitride, of the directional couplers, and another one is the background material SiO2. And if you would like to see if there is any divergence in your simulations, you would like to debug it. So one good thing to have is also have a time movie monitor that you can add. It is present in the drop-down menu. You can see that there is a movie monitor. So what movie monitor does is it allows you to accumulate, it gives a video file output where you can see where the pulse is going to travel. So for example, if your injection direction is wrong, you would see the pulse going in the positive y-axis, and then you can debug it very easily. Otherwise, you'd be blind. You won't see any power in both of your monitors in the waveguides. So it is very good to have this one, and you can indeed click on the monitor and then adjust the size of the monitor. And then if your simulation time was not enough, if 1000 femtosecond was not enough for the light to travel from here to here, you would see the pulse getting cut off in the middle of something, so that you can increase your total simulation time and then run your simulations again. And then I think now we are done with the simulations, and I hope I had done everything correctly. So you should be, if I click run, first then I can see over here that there is an option to check the simulation. So yeah, yeah, so boundary conditions. So what happens is when you added FDTD, the default boundary conditions itself are PML, so I didn't explain that. There was this boundary conditions over here. So you can see that the boundary conditions is on both the positive side of your X and negative side of your X, you have PML, and the same on your Y and Z. So you can have your boundary conditions to do the same. And then there is also another option for symmetric boundary conditions. That is, if you, as you can see, our structure has symmetry along the Z equal to 0 plane. So you can just click a symmetry, and then you can choose like Z minimum and Z maximum to be symmetric. But then if you even don't do this and then just have PML, you would get the same results, but it will take double the time for your simulation to run. So it's the same. You can compare it if you get the same results or not. And the thing is, I added a source, but I never defined, I realized that I never defined the mode that I'm going to excite into the waveguide. So to look into the mode that is going to be excited in the waveguide, I again click edit, and then I see that I have some options over here. So either you can just ask Lumerical to excite the fundamental mode. It will just excite the mode that is like suited for your waveguide. It can be T or TM, but then there is an option to excite the first fundamental TE mode and the first fundamental TE mode. But then I would like to have a look at what modes are supported in this waveguide. I can click user select and select the number of modes. There's an option to select the mode. You can left click, and then you see that I would like to, you have an option for the frequency, wavelength, and number of trial modes. And I see that the frequency is wrong. This frequency needs to be set into your FDTD simulation region. So let's go and select, this frequency needs to be set into your source. So there is an option called as frequency and wavelength tab. Since we are working in the telecom band, which is like 1.55 micron, so there's an option to center your frequency at 1.55. And you can, ideally, I would like to know the device performance around this. But then again, I'm going to do pulse propagation, so I cannot have a zero span around this region. So it needs to always have some span, because we are working in the time domain, and there is a finite spectral width that you get when you Fourier transform the pulse. So the wavelength span of 0.2 is like the minimum. You can click apply, and you would see that it should change to 1.5. Let me click OK. And then, yeah, there was some hiccup, but then I just click OK, and then reopen it. You can see that there was like 1 point. So then now the spectrum is around this. Like if you even try to reduce it, I think your pulse will just be broadened because of Fourier transform properties, but then it would be the same. I think 0.2 was the minimum which you can get. So you set the frequency parameters, and then you go back, and you would like to see the modes that are supported in this system. So now you see that the frequency is around 194 terahertz, that is 1.55 micron, and you would like to see how many modes that are supported. I would like to see the first 3 modes that are probabilistically excited in the system. So I can just click 3, and it is going to search the modes. So I can go down, and there's an option to click calculate modes. It will see, you can see that actually the size of your source was not the size of the source, the y dimension and the x dimension of your source was not properly set to the aspect ratio of your monitor. So you see that the waveguide, which I don't know if you can see, is like given in blank. It is squeezed, but actually this is 0.8 micron, and this is even larger than 0.8. So it is actually squeezed in the y direction, in the z direction on this plane. So the mode is like actually around this one. But then you can change the aspect ratio and play around with it to get like proper one based on this side, changing your source size. So I see that there is this mode index that is excited with this polarization fraction and TM fraction. And there is other higher order T modes that are also possible. And this is like TM mode that is also possible. But then I would like to excite the first fundamental T mode. So I click select, and then I click apply. So now I have set the source that I need to excite, and I have set the boundary conditions, the size and monitors, and the wavelength. So I am good to run the simulation, but before running the simulation, I can check how much memory requirements and RAM it's going to consume by clicking the button over here. Okay. I think this will take some time, but then, yeah, I think I just realized when you imported the silicon nitride MDF file, you just imported the refractive index as a function of wavelength, and these are like an array of values. You have 100 wavelengths and 100 refractive index options, but then your spectrum was like broadband from 1.4 to 1.6 micron. What you would need to have is refractive index for any values that you would like to simulate for. So what you would need to do is you need to do an interpolation of this refractive index value, which we didn't do, which I will just show how to do it. But before that, I show the total memory requirements that you need to do. Is it's going to save like data collection of 5 MB, and the running simulation will take 2 GB of RAM. It's fine because your phones now have 16 GB of RAM, and and you can just collect the data and store over here. Yeah, and regarding the material interpolation, this is important. Otherwise, your simulation will just give incorrect results. What you need to do is go to the material explorer option, and this is just going to give the material that you have used into your GDS into your Lumerical file. That is the silicon nitride, and you see that it set everything fine, 1.55 micron. But then if you click show and fit and plot, you would see that around 1.5. Yeah, it had in fact fitted around 1.5. You need to make sure that your material interpolation is done based on your values that you imported. For example, the green dots are the numbers that was inside the .mdf file, and the blue line is the one which it is going to use for the epsilon is like permittivity, and it is directly related to refractive index. So this is important, and it took like 6 polynomial constants to fit this polynomial, and it had actually fitted not across all wavelengths. Like it won't be fitted around this 0.9 micron. You see no blue line because this is dependent on your center wavelength and span. So usually this is not done automatically just because I selected the source to be lambda 1.55, it ran, it fitted it, but it might be different for you guys. So you need to make sure that it is done. And then you can click go back to material files and then click OK, and then it would have saved. And we can just click run and it will run in the background. Okay, I had never saved this file. Okay, I'll save this as tutorial session. I have it will show like some 30 minutes or 50 minutes. It will show a large enough time, but then this is because I set it like 1000 frames per second, but in fact it will converge faster and it should run. Basically, I tried to optimize the device parameters, coupling length as 30 and waveguide width as 1.4 micron. This is not realistically correct. This device won't work, but it will help you guys to simulate it faster. Okay, so it will like take some 10 minutes or 11 minutes to run. But then, okay, I think I was a bit slower because it went like more than 14 minutes, but then I don't know if Antonella, because if they start doing the simulations, it will take a bit of time. What do you do? Yeah. Okay. Yeah, I can do the bus-resonator coupling quickly again after lunch, and then they can do both the exercises together. Join the exercise sessions. Yeah, so basically you have a file called as exercise1.pdf. So it contains the questions and the expected results, and you also have access to the working Lumerical file with the Lumerical results stored. So that is why the size of files is 300 MB. And if you go through the exercises that I created, you have this both the solutions and the file solutions to the simulation files. So you can just look around and try what you have done by just debugging it. All right, we can do it after the lunch in the exercise session for the second part. Yeah.
Do you have any questions so far? Have you covered?
Yeah.
Background materials.
Okay, so basically we have some method, we get the cross section of it, but then this is like presented. This is your FDTD boundary. But then you want to have some SiO2 that is present everywhere. So you can choose your background material for the entire FDTD region with SiO2 as your background material. No, I mean, this is realistic. If you had air, you can have it. I mean, we have some materials, lithium tantalate with air cladding. So basically, like you have lithium tantalate from air, and based on that you can have whatever material you want. And at that time, what you need to do is you need to add a rectangle. You need to add a rectangle slab with that much thickness, like 300 nanometer or something, and then choose the property for that material. You would choose SiO2 as property for this material, and then choose background as air. So you have your device overlay options, so which is going to supersede and which is going to. No, you won't have two different backgrounds. You would have air as your background and your rectangle slab as your SiO2. Okay. Yeah, because your GDS file, you just import only the top layer. So you have the option to import the rectangle directly. I think I'll show you how to do like structures directly without any GDS file, directly in Lumerical. Actually, there's an option called structures. It has different options. Okay.
So you're sure that you use very simple installation?
Yes.
In which case we can seek fix less.
What?
There are options. on
Yes,
this
exactly.
one where-
What about Y? Yeah, you can consider Y symmetry, but then I'm pumping it from the
From one side on.
one side only. I'm not pumping it on the right side.
So in
So
which case you can seek say one.
yeah, in this geometry, if you are pumping it both on left side and right side,
But
top
the structure
waveguides.
is symmetrical.
Yeah. Yes, but if you're
The
pumping
pump
it,
is not symmetrical.
pump is not symmetrical. If you pump both on the top two waveguides, then you would have Y symmetry.
You can do it. Your simulation.
You can do it, but this is the device under consideration is with only one source.
But if it's not a simulation, then
But you're not going to pump it on both the waveguides.
okay, the
On the
wavelengths
chip.
are the same. Then it's no use.
Realistically, for a directional coupler, you just pump it on one of your waveguides.
But if you
And
pump
then
on both sides, what are the
that is left for another exercise. That is a different question entirely. The device under consideration is with one mode source. Indeed, if you had two mode sources that were pumped on both the sides, then you would have Y symmetry and Z symmetry. It would reduce your simulation time to 1/4. It's fine, but that is huh? Well, I don't know. We need to simulate it. Sorry? Yeah, that is too much. I know. But it won't be exactly.
Yeah. Okay.
Then check this. This is you can actually see. So this is
Yes, so for importing the materials, there are certain default materials that are present, but then our lab uses silicon nitride, which is not present or might be present, but the refractive index is not very accurate to what we have. So we have measured the refractive indexes in the lab and created the text file that is present inside this. So that is why it has item movie or design. So it has that material. You won't have it if you don't import it. No, it says just saying that it's not 24.5, but it's 1.5 times. How many times not the minimum value? Once it's below 1, you have. No, it's going below 1. Total power inside
My brother. Yeah. Because I am.
That's yeah, I said. Let's also basically tracking every one of the default. But the default method is never change.
And all.
don't know, I think I did.
You can come if you want, I have experts. Good reading thing, I'll pass you on.
No, I want to see.
Okay. And you go to
I think this is about everything.
Are you sure?
System is an outburst.
Because it is like half. Yes, one texture is so first half texture is for negative, the next half texture is for Our EPFL.